You are holding right now roughly 10 billion atoms in the tip of your finger. That number sounds large until you consider that a single teaspoon of neutron star material would weigh approximately 1 billion tons, more than the combined mass of every human being who has ever lived, every building ever constructed, every ship ever launched, every mountain ever named, compressed into a volume the size of a sugar cube sitting on your kitchen counter. That is not a metaphor designed to impress you. That is a measured, verified, physical fact about the universe we inhabit. And the question is not merely how something like that exists. The question is, what would actually happen to you, to your body, to your atoms, to the very concept of your continued existence, if you fell into one? If you enjoy videos that take the most extreme corners of the known universe and drag them, carefully and precisely, into human terms that translate the language of physics into something you can actually feel, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common thing people believe about neutron stars is that they are simply very dense, very small stars, a kind of compressed version of the Sun, the same object in a smaller package. Dangerous, the way a fire is dangerous. Something you could describe on a single spectrum, from not so hot to very, very hot. That framing is wrong. Not incomplete, not oversimplified. Wrong. A neutron star is not a star in the way we use that word for the Sun. It does not burn. It does not fuse hydrogen into helium. It does not generate energy through nuclear combustion at its core. A neutron star is something categorically different from every other object most people have ever heard of. It is a state of matter, a condition of existence. It has no parallel in ordinary physical experience, and almost no parallel anywhere else in the observable universe. To understand what happens when you fall into one, you need to first understand what it actually is. And to understand what it actually is, you need to start not with the neutron star itself, but with the moment it was born. Every atom of iron in your blood was forged inside a star. That sentence has been repeated so often, it has nearly lost its power to shock, so let's be precise about what it means. Roughly 8 billion years ago, somewhere in the Milky Way, a star, somewhere between 8 and 20 times the mass of our own Sun, was living out the final stages of its life. For millions of years, 10 million, perhaps 20 million, a span of time so vast that if you compressed it into a single calendar year, all of recorded human history would occupy the last 2/10,000ths of a second. That star had been fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into oxygen, neon, magnesium, silicon. Each fusion reaction releasing energy, each energy release holding the star up against the crushing inward pull of its own gravity. The star was, in a very real sense, a negotiation. Gravity pulling inward, energy pushing outward. For millions of years, gravity and energy held each other in a kind of cosmic standoff. Then the star reached iron. Iron is the end of the road for stellar fusion. Every fusion reaction up to iron releases energy. The products weigh slightly less than the ingredients, and that missing mass becomes energy, the energy that holds the star open. But iron is different. To fuse iron into anything heavier requires you to put energy in rather than get energy out. Iron is the point at which the universe stops paying dividends on stellar fusion. And so, on the day the core of that massive star becomes pure iron, A solid iron sphere, roughly the size of Earth, roughly 1.4 times the mass of our Sun, sitting at the centre of this stellar giant. The negotiation ends. In less than 1 second, not 1 minute, not 1 hour, 1 second, the entire iron core collapses. The outer layers, no longer supported, fall inward at roughly a quarter of the speed of light. 25% of the speed of light, inward, in a single catastrophic implosion that releases more energy in that 1 second than our Sun will release across its entire 10 billion year lifetime. The outer layers slam into the now collapsing core. The resulting shockwave blows the whole star apart in one of the most violent events the universe produces, a core collapse supernova. What is left behind after the light fades and the debris cloud expands outward across light years is the neutron star. It is, in essence, the core that survived. The iron that collapsed did not collapse into nothing. Under the force of that infall, pressures so extreme they have no earthly analogue, electrons and protons were forced together. Electrons and protons, which are normally separate particles, were pushed so close together that they merged, each electron combining with each proton to produce a neutron. Neutrons are particles with no electrical charge, and crucially, neutrons can be packed together with none of the electromagnetic repulsion that keeps ordinary matter spaced out. The result is an object that is, in its interior, almost pure neutrons, a sphere of densely packed neutrons, roughly 10 to 13 kilometers across. 10 to 13 kilometers, that is smaller than many cities. The city of London, measured roughly from its eastern to western limits, is wider than a neutron star. The island of Manhattan is roughly 20 kilometers long, nearly double the diameter. You could drive across a neutron star, if driving across a neutron star were not the most immediately lethal act conceivable in the physical universe, in less than 10 minutes. And yet, this object, this city-sized remnant, contains between 1.1 and 2.3 times the mass of our entire Sun. To give that scale a human anchor, our Sun contains 333,000 times the mass of Earth. Earth contains approximately 6 times 10 squared kilograms of matter, 6 followed by 24 zeros. Our Sun contains 333,000 times that. A neutron star contains between 1.1 and 2.3 times the mass of our Sun. In an object, you could walk around in a morning, if walking were possible, if you were not immediately vaporized, torn apart at the atomic level, and then compressed into something that no longer resembles matter as we understand the concept. This is the object. This is what you are falling into. But before we begin the descent, there is something we owe to the history, to the people who first glimpsed this object, not with telescopes, but with mathematics and courage. Because the neutron star was theorized before it was discovered, and the gap between the theory and the confirmation is one of the strangest stories in the history of science. In 1932, James Chadwick discovered the neutron, a particle with roughly the same mass as a proton, but with no electric charge. The discovery was announced in February of that year, and within months, 2 young astronomers named Walter Bade and Fritz Zwicky had already imagined what a star made entirely of neutrons might look like. In 1934, they published a paper, one of the most prescient documents in the history of astrophysics, in which they proposed that supernovae, the colossal stellar explosions that had been observed but not explained, were produced by the collapse of ordinary stars into neutron stars. The paper was brief. It was largely ignored. The physics community in 1934 had no particular reason to take seriously the idea of a star made of neutrons, an object whose density exceeded anything anyone had ever conceived of, an object for which no observational evidence existed. Neutron stars joined the long list of theoretically possible things that everyone assumed were probably not real. They stayed on that list for 33 years. On November 28, 1967, a 24-year-old graduate student named Jocelyn Bell was analysing the paper chart output of a radio telescope she had helped build in Cambridge, England. The telescope was designed to look for quasars, distant, compact, energetic objects that emit radio waves. Bell noticed something odd in the data, a regular, repeating signal, pulsing with a period of 1,337 3-seconds, so regular that the researchers initially nicknamed it LGM-1, Little Green Men 1. The signal was so perfectly periodic, so much more regular than any known astrophysical process, that for a few weeks the possibility of an artificial origin of a signal produced by intelligence was taken seriously enough to be discussed. It was not taken seriously enough to be published, but it was discussed. It was not Little Green Men, it was a neutron star, a rapidly rotating neutron star emitting a beam of radio waves from its magnetic pole that swept past Earth once per rotation, like the sweep of a lighthouse beam. The object was a pulsar, the name coined shortly after the discovery, and its extraordinary regularity was not the product of intelligence, but of physics. A body rotating 0.75 times per second. So massive that no conceivable force could perturb its rotation by a measurable amount on human timescales. A lighthouse run not on electricity, but on angular momentum, on the stored rotational energy of a stellar core, spinning in the cold dark, broadcasting its existence to anyone with a radio telescope and a patience to look carefully at the noise. Zwicky and Beatty had been right. The neutron star was real. And Bell's discovery, for which her supervisor, Anthony Hewish, received the Nobel Prize in 1974, in one of the most controversial Nobel decisions in physics history. Since Bell herself was excluded, despite being the one who found the signal, opened a window onto the most extreme physics accessible to observation in the known universe. It was the beginning of an entire field. But the story of neutron star discovery does not begin and end with Bell's radio telescope. It runs in parallel through a second observational tradition entirely, one operating in a different wavelength and driven by different instruments: X-ray astronomy. In the early 1960s, rocket-borne Geiger counters, launched above Earth's atmosphere, since X-rays are absorbed by the atmosphere and cannot be detected from the ground, found that the sky was not dark in X-rays. There were sources, bright ones. The most remarkable among them, Scorpius X-1, discovered in 1962 by a rocket flight led by Riccardo Giacconi, who would later win the Nobel Prize for his foundational contributions to X-ray astronomy, was emitting X-rays 100 times more powerfully than any ordinary star. It was clearly not powered by nuclear fusion. Something else was happening. Within a decade, the identification of SCO-X-1 and objects like it as accreting neutron stars in binary systems became compelling. The Uhuru satellite, launched in 1970, the first satellite dedicated entirely to X-ray astronomy, catalogued 339 X-ray sources across the sky and identified pulsing X-ray sources, neutron stars, in binary systems whose rotation produced regular pulses in the X-ray flux, just as isolated radio pulsars produced regular pulses in radio waves. These X-ray pulsars were neutron stars being spun up by accreted angular momentum, flashing in hard radiation, with each rotation as the accretion hotspot, the region where infalling matter struck the surface, swept past the line of sight to Earth. In 1974, Russell Hulse and Joseph Taylor discovered the first binary pulsar, PSR B191 3+16, a pulsar in a binary system with another neutron star. This was a gift of extraordinary scientific value. Two massive compact objects in a tight orbit, one of them a precisely ticking radio pulsar whose arrival times could be measured to a millionth of a second precision. This was, in effect, a laboratory for general relativity. Einstein's theory predicted that the orbiting pair would lose energy for the emission of gravitational waves, ripples in spacetime caused by their acceleration, and that this energy loss would cause the orbit to shrink measurably over time. Hulse and Taylor measured the orbital period and the rate at which it was changing. The orbit was indeed shrinking at exactly the rate predicted by general relativity's gravitational wave emission formula. The agreement between theory and observation, accumulated over years of pulsar timing, was precise to better than 1 part in 1,000. This was the first evidence, indirect but incontrovertible, for the existence of gravitational waves. Not a detection of the waves themselves, that would come 4 decades later, but a measurement of their effect on the orbit. The Nobel Prize came in 1993, and it was deserved without controversy. Hulse and Taylor had confirmed, using a pair of dead stars 21,000 light-years away, that Einstein's general relativity was correcting a regime of strong gravity and high velocities that had never previously been tested. They used a neutron star as a precision instrument to probe the geometry of spacetime. In the decades since, the catalogue of known neutron stars and pulsars has grown from 1 to thousands. We have found neutron stars in the centres of supernova remnants, the beautiful Crab Nebula, the expanding cloud of gas from a supernova observed by Chinese and Arab astronomers in 1444 C, contains at its centre a neutron star rotating 30 times per second, the Crab pulsar, still young and hot and powerful nearly 1,000 years after its birth. We have found neutron stars and globular collections, the dense spherical collections of ancient stars that orbit the outer Milky Way, where the high density of stars means that neutron stars frequently encounter companions and undergo episodes of accretion that spin them up to millisecond periods. Some globular clusters contain dozens of millisecond pulsars each. We have found neutron stars and other galaxies detected as bright X-ray sources in observations by the Chandra X-ray Observatory and XNM Newton. We have found neutron stars whose X-ray emission oscillates during bursts with the precise rotation frequency of the star, allowing us to measure the rotation rate of a star in the middle of a thermonuclear explosion on its surface. We have found double neutron star systems, neutron star white dwarf binaries, neutron star black hole binaries. We have found neutron stars so close to their companion stars that the neutron star surface is nearly touching the companion. Each discovery has added a new constraint, a new measurement, a new data point in the global effort to understand what these objects are. And yet, for all of this richness, the interior remains inaccessible. We see only the outside. We measure the pulse, we count the photons, we hear the gravitational wave, and from all of these signals, we work backward, through theory and simulation and mathematical models toward the interior. It is like trying to understand the engine of a car by listening to the sound it makes from outside. We have gotten very good at it, but we have not yet opened the hood. In the decades since that November night, we have catalogued over 3,000 pulsars in our galaxy alone. We have found neutron stars in binary systems, in globular clusters, at the centres of supernova remnants. We have found them spinning faster than any other object in the universe. We have found them with magnetic fields 1 trillion times stronger than Earth's. We have found them merging, colliding, and collapsing into black holes, and we have watched those mergers in gravitational waves. And yet, for all of this observational richness, the interior of a neutron star remains the least directly accessible region of the observable universe. We cannot send a probe, we cannot take a sample, we cannot look inside. We can only listen to what the outside tells us, the timing of pulses, the spectrum of X-ray emission, the shape of gravitational wave signals, and deduce from those indirect messages what is happening in matter more compressed than anything a laboratory on Earth can produce, or even closely approximate. Now let us talk about the approach. Before you ever reach the surface, before the first truly extraordinary things happen, the journey toward a neutron star is itself a sequenced escalating violence that would end a human life, and then a human body, and then the atoms of that body, many thousands of kilometers before touchdown. But understanding the approach is essential because it reveals something profound about the nature of gravity that most people never quite grasp. Imagine you are in space, in some future era, traveling through the galaxy. For the purposes of this thought experiment, you have been provided with a ship capable of surviving anything, a hypothetical vessel of impossible durability, a thought experiment craft. You and the ship are falling toward a neutron star from a great distance, perhaps from a point a few thousand kilometers away. At this distance, the neutron star looks, visually, like a small but intensely bright point of light. Neutron stars radiate. Many of them radiate X-rays with such ferocity that, were you unshielded, the X-ray flux alone would deliver a lethal dose of radiation in a fraction of a second. The youngest neutron stars, still hot from their birth in a supernova only thousands of years ago, a young neutron star, by cosmic timescales, is one that formed around the time of the Roman Empire, can have surface temperatures of 1,000,000 degrees Kelvin. 1,000,000. The surface of our Sun is approximately 5,778 Kelvin. A young neutron star surface is more than 170 times hotter than the surface of the Sun. The radiation pouring off that surface is not light you can see. It is X-rays, and it is lethal at distances that would qualify, on any normal scale, as quite far away. But let's set radiation aside for a moment, because it is, in a sense, the least structurally interesting thing about this journey. Let's talk about gravity, and what gravity actually does at these extremes, because this is where most intuitions fail entirely. When physicists describe gravity near a neutron star, they do not use Newton's equations. They use Einstein's. And the difference between those two frameworks is not merely mathematical precision, it is the difference between a map and the territory. Newton described gravity as a force acting between objects across distance, a kind of invisible rope pulling things together. Einstein described something richer, stranger, and ultimately more accurate. Gravity, in Einstein's framework, is not a force at all. It is the curvature of space-time, the four-dimensional fabric of space and time itself, caused by the presence of mass. Objects in curved space-time follow the most natural paths available to them, which we perceive as acceleration toward the mass causing the curvature. Near a neutron star, space-time is curved so severely that the distortion is not a small correction to Newtonian physics. It is the dominant feature of reality in that region of space. Think of it this way. Imagine you are walking across a vast rubber sheet, perfectly flat, stretched taut. Your steps are straight. Your path is a straight line. Now, someone places a bowling ball in the center of the sheet. The sheet deforms, curves downward in a bowl shape around the ball. If you now try to walk in a straight line near the bowling ball, the shape of the sheet curves your path. You cannot walk straight anymore. The surface itself is curved, and your feet follow it. You have not been pushed. The geometry of this space you are walking through has changed. That is gravity in Einstein's description. The bowling ball is the mass. The rubber sheet is space-time. The curvature of the sheet is the gravitational field. Near a neutron star, the bowling ball has been replaced by something whose mass would punch through any rubber sheet ever conceived. An object so dense that the curvature it produces is not a gentle bowl, but something approaching a vertical cliff. A pit so steep that climbing out of it requires velocities approaching the speed of light itself. This is what you are falling into. Not a region of strong pulling, a region of extreme geometry. But the story of neutron star discovery does not begin and end with Bell's radio telescope. Consider the escape velocity. Escape velocity is the speed an object needs to be travelling in order to escape a gravitational field without further propulsion, to be thrown upward hard enough that it never falls back down. On Earth, escape velocity is approximately 11.2 kilometers per second. On the surface of the Sun, it is 617 kilometers per second. On the surface of a neutron star, escape velocity is somewhere between 100,000 and 150,000 kilometers per second, roughly 1/3 to 100% of light. 1/3 of the speed of light. To escape the surface of a neutron star, you would need to be launched at speeds between 1/3 and 1/2 the speed of light. Nothing biological survives even a fraction of such acceleration. Nothing mechanical we have ever built survives it. And this escape velocity figure has a profound implication that we will return to. Light itself, travelling at the full 300,000 kilometers per second, that is its maximum possible speed, barely gets out. It escapes, but barely, and in doing so it pays a price. Gravitational redshift. The light that leaves the surface of a neutron star arrives at distant observers shifted so dramatically toward longer wavelengths that much of the X-ray radiation emitted at the surface becomes observable as lower energy radiation by the time it roses its soar, reaches us. The light has been tired out by climbing the gravity well. There is something worth pausing on here. When we say that light is redshifted, shifted toward longer, redder wavelengths, as it climbs out of a gravitational field, we are saying something that sounds like a mere technical detail, but is actually a window into the deepest architecture of space-time. Light carries energy. Its energy is proportional to its frequency. Higher frequency, higher energy. Gamma rays are high frequency, high energy light. Radio waves are low frequency, low energy light. When light leaves the surface of a neutron star and reaches a distant observer with lower frequency than it had at emission, it has lost energy. Where did that energy go? It went into declining the gravitational potential. The light paid a toll in energy for escaping. And since frequency is directly linked to how fast the oscillations of the electromagnetic wave are counting, a lower frequency means those oscillations are counting more slowly. Time has slowed. The clock built into the light wave, the oscillations themselves, has been slowed by the gravitational field. This is not an analogy. This is what is happening physically. Clocks run slow in strong gravitational fields. All clocks. Atomic oscillations, heartbeats. Thought itself, were you present, would proceed more slowly relative to a distant observer watching you from afar. This is gravitational time dilation, and near a neutron star, it is not a small correction. It is a large, measurable, fundamental feature of the geometry you are moving through. The gravitational redshift of a neutron star is, in fact, one of the tools we use to measure its properties from afar. When we observe X-ray spectral lines from the surface of a neutron star, the characteristic emission lines of iron or other elements in the hot atmosphere, whose energies we know precisely from laboratory measurements, we can compare the observed energies to the expected energies and measure how much they have been redshifted by the gravitational field. From the redshift, using the equations of general relativity, we can constrain the ratio of the neutron star's mass to its radius, the compactness. Combined with independent mass measurements from orbital dynamics, this gives the radius. Combined with the radius and mass, this constrains the equation of state. The light that climbs out of the neutron star's gravity well, tired and reddened by the journey, carries encoded in its spectrum the fingerprint of the gravity it escaped. We read that fingerprint with X-ray telescopes. We translate it, with mathematics, into statements about nuclear matter at densities no laboratory can reach. The NICER instrument, the Neutron Star Interior Composition Explorer, mounted on the International Space Station since 2017, was built specifically to do this kind of measurement. By precisely tracking the X-ray emission from hotspots on the surfaces of millisecond pulsars as the stars rotate, and modelling how the light from those hotspots is bent by the strong gravity before reaching the telescope, NICER extracts both the mass and the radius of the neutron star simultaneously. The bending of light by the neutron star's own gravity, the same effect that makes more than half the surface visible at once, leaves an imprint on the light curve of the pulsar that depends on the star's compactness. A more compact star bends light more strongly, changing the shape of the pulsar, while light is bent on the right side. A more compact star bends light more strongly, changing the shape of the pulsar, and contains a full bend on the right side. NICER has made measurements of several millisecond pulsars, providing the most precise radius constraints available for neutron stars. And those constraints are already beginning to narrow down which equations of state are consistent with reality. The work is ongoing. Each measurement is a clue. The picture sharpens. Now, as you approach from a few hundred kilometers out, you begin to notice something else. Your instruments register. The gravitational gradient across your ship is detectable. This is the precursor to the most immediately destructive phenomenon of the entire journey. That phenomenon is tidal forces, and it will be, for you as a physical body, the first thing that kills you. Tidal forces are, in principle, something you already know. The tides in Earth's oceans are caused by tidal forces. The moon pulls on the near side of the Earth slightly more strongly than it pulls on the centre of the Earth, and slightly more strongly on the centre than on the far side, because the near side is closer to the moon and gravity diminishes with distance. The result of this differential pull is that the Earth and the oceans on its surface is slightly stretched in the direction of the moon. The bulge you get on the near side and the corresponding bulge on the far side are the tides. The differential is tiny on a cosmic scale. The moon's gravity at the near side of Earth is only about 6.9% stronger than at the far side, and this produces tides averaging around 0.5 meter in the open ocean. Now apply that logic to a neutron star. The neutron star's gravitational field is incomparably stronger than the Moon's, and it falls off with distance just as all gravitational fields do. If you were oriented feet first toward the neutron star, the pull on your feet is significantly stronger than the pull on your head, because your feet are closer. The result is a stretching force along your body's long axis. Astrophysicists call it spaghettification when they apply it to black holes, and it applies equally to neutron stars. Your body would be stretched, first uncomfortably, then painfully, then catastrophically, into something resembling a long, thin strand of dialogical material. Not metaphorically, literally. The atoms in your feet would be accelerating more rapidly toward the neutron star than the atoms in your head. Your body, which has no tensile strength remotely sufficient to resist this differential, would be torn apart. At several hundred kilometers out, your body begins to register the tidal gradient. The neurons in your brain notice nothing yet, because the gradient across 2 meters of human height at this distance produces only a fraction of a % difference in gravitational pull. At 100 kilometers, the difference is more significant. You feel an unpleasant pulling sensation in your limbs, as though something enormous below your feet were trying to elongate you. At 50 kilometers, depending on the neutron star's exact mass, you are beginning to experience structural failure, bones cracking, connective tissue tearing, the soft architecture of your body being drawn apart along the radial axis. At 20 or 30 kilometers, the tidal gradient across your body height is tens of thousands of gramses. Your bones, your tendons, the muscles, every structural material in your body has a tensile strength measured in megapascals. The tensile stress trying to pull your feet away from your head at 20 kilometers from a neutron star is measured in gigapascals, 1,000 times higher. You do not experience this as a gradual stretching. At these force levels, the structural failure is instantaneous and total. In the time it would take a single neuron to fire, you are no longer a body. You are a stream of atoms and molecules, ionizing as they accelerate, glowing as they compress. But the atoms of your body survive, initially. Atoms are much harder to destroy than people. Your body, disrupted into its constituent atoms and molecules, continues to fall. The tidal forces that pulled your body apart do not stop operating. They continue to operate on the cloud of matter that was you, stretching it further, elongating it along the radial direction of fall, creating a thin stream of infalling material. This stream falls faster and faster, compressed in the transverse directions by the tidal gradient, and stretched radially, heating as it compresses. The heating is real and rapid. As the matter falls through the neutron star's intense magnetic field, a field 100 million to 100 billion times stronger than Earth's, the charged particles spiral along field lines, radiating energy as synchrotron radiation, a form of electromagnetic emission produced when charged particles are forced to move in curved paths by a magnetic field. The stream glows, it radiates. It is visible from enormous distances as a source of X-rays and potentially gamma rays, long before it reaches the surface. But the story of neutron star. Now let us talk about what is happening to the space-time geometry as you approach still further, because something else is going on. Something that has no analogue in everyday experience, and that requires a specific image to make tangible. A rotating massive body, according to general relativity, does not simply curve the space-time around it, it drags it. If you have ever stirred honey with a spoon, You know what it looks like when a solid object moves through a viscous fluid and pulls the fluid along with it. Frame dragging, which physicists call the lens-theory effect, is the analogous phenomenon in general relativity. A rotating massive body pulls space-time along with it as it turns, like the spoon and the honey. But the honey, here is the four-dimensional fabric of the universe. Near a rapidly rotating neutron star, space-time is not just curved, it is being dragged, twisted, rotated. If you were trying to hover above a rapidly rotating neutron star in a fixed position in space, firing rockets, attempting to stay in place, you would find that you cannot stay truly fixed relative to the distant stars. The space-time around the star is rotating, and you are in it, and it is carrying you around, whether you like it or not. You would need to fire your rockets continuously in a specific direction just to prevent being dragged around the star by the rotating geometry of space-time itself. This effect has been measured on Earth using the Gravity Probe B satellite, which flew in a polar orbit around Earth from 2004 to 2005 and measured the precession of gyroscopes caused by Earth's frame dragging effect, a precession of about 0.039 arc-seconds per year, roughly 100 million times smaller than a single degree. Near a millisecond pulsar, this effect is not 100 million times smaller than a degree per year. It is significant. The space-time near a millisecond pulsar is visibly, measurably, dynamically rotating. As you enter the region within a few stellar radii, something else changes: the structure of the light itself. On a neutron star, gravity is strong enough to bend light significantly. A photon, a particle of light, travelling near the surface of a neutron star, follows a curved path through the warped space-time. This has a remarkable odd civilization. You can see more than half the surface of a neutron star at once. On Earth, if you stand in front of a sphere, you can see exactly half of it, the hemisphere facing you, with the boundary being the great circle at the sphere's edge. But around a neutron star, the light coming from the far side of the star is bent around the star by gravity, so it curves toward you. You see a distorted image of the star in which more than half the surface is visible simultaneously, the far side light bent around the edges by the space-time curvature. The precise fraction of the surface visible depends on how compact the neutron star is, on the ratio of its mass to its radius. For a star with the canonical 1.4 solar masses in a radius of 10 kilometers, roughly 70% of the surface is visible to a distant observer at any moment, compared to the 50% you would see for a sphere with no gravity. If the star were even more compact, closer to the black hole limit, this fraction could approach 100%. You could, in principle, see the entire surface simultaneously. Not because the star has become transparent, but because the light from every point on the surface has been bent so severely that it all reaches you, regardless of which side of the star it came from. Now add rotation. A rotating neutron star with a hotspot, a brighter, hotter region on the surface, perhaps near the magnetic pole, produces a pulsation in its X-ray brightness as the hotspot rotates in and out of view. But because of gravitational lensing, the hotspot is never completely hidden. Even when it rotates to the far side of the star, some of its light is bent around the edge and still reaches you. The pulsation is therefore not a simple on-off switching. The hotspot never fully disappears. The shape of the pulse profile, how the brightness varies smoothly through the rotation cycle, with what depths of minimum and what shape of peak, encodes the geometry of the star, the location of the hotspot, and the compactness of the object. This is exactly what NICER exploits. The pulse profile is a map of the geometry. The geometry is a constraint on the physics. The physics is what we want to know. And there is still more to the visual environment. As you approach the neutron star, you are also moving through a region of extraordinary electromagnetic intensity. The magnetic field lines threading the magnetosphere, the region of space dominated by the neutron star's magnetic field, extending from the surface outward for tens to hundreds of kilometers, are not static. They are rotating with the star, and their rotation drives electric fields that accelerate charged particles to relativistic velocities. These particles, spiraling along the magnetic field lines, emit synchrotron radiation in sweeping beams, the radio and X-ray pulses we detect from pulsars. They also emit copiously at shorter wavelengths: optical, ultraviolet, and gamma ray. The region within a few stellar radii of the neutron star is not dark and quiet. It is a storm of relativistic electrons and positrons, of X-rays and gamma rays, of magnetic field lines being swept around 716 times per second. It is the most intense electromagnetic environment in the observable universe, outside of the immediate aftermath of the Big Bang. In this environment, something happens that is predicted by quantum electrodynamics, the quantum theory of the electromagnetic force, but has never been observed in a laboratory: photon-photon scattering. In vacuum, two beams of light simply pass through each other without interacting. But quantum electrodynamics predicts that at sufficiently high electromagnetic field strengths, the vacuum itself becomes non-linear. It behaves as if it had an index of refraction, as if it were a material medium through which light propagates. This effect, called vacuum birefringence, means that light polarized in different directions relative to the magnetic field travels at slightly different speeds through the magnetized vacuum near a magnetar. The two polarization components of the light become separated in phase, and if you could measure the polarization state of the light arriving from the neutron star, you would see evidence of this quantum vacuum effect in the rotation of the polarization angle. In 2017, a measurement of the optical polarization of the isolated neutron star RxJ 1856.5-3754 using the Very Large Telescope in Chile found evidence consistent with vacuum birefringence, the first hint in an astronomical observation of a quantum electrodynamic effect that requires field strengths impossible to produce in any earthly laboratory. A neutron star's magnetosphere is conducting experiments in quantum field theory that we cannot replicate, and broadcasting the results in polarized optical light. And we are measuring that polarization with telescopes and reading the results of quantum vacuum physics at its most extreme. Now, let us go deeper, past the surface into the layers of this extraordinary object, following the descent into matter more compressed than anything in ordinary experience. The surface of a neutron star, and surface here is a somewhat misleading term, since it implies a boundary as clear and solid as the ground beneath your feet, which is not quite what exists here, is where the atmosphere ends and the crust begins. Let us talk about the atmosphere first, because a neutron star atmosphere is itself one of the stranger things in the universe. A neutron star has an atmosphere. It is extraordinarily thin, perhaps only a few centimeters thick on some neutron stars, perhaps a few meters on others. This atmosphere consists primarily of hydrogen and helium that have not been swept away by the intense radiation, plus possibly heavier elements. The temperature at the top of this atmosphere is millions of degrees. The temperature, measured over those few centimeters of vertical extent, drops by many orders of magnitude. The density gradient is absurd. The pressure at the base of this atmosphere, where it meets the crust, is already many millions of times greater than the atmospheric pressure at sea level on Earth. This pressure is generated by the enormous surface gravity. The surface gravity of a neutron star is approximately 100 billion to 200 billion meters per second squared, between 10 billion and 20 billion times the surface gravity of Earth. If you were to stand on the surface of a neutron star, and no physical object we have any concept of could exist as a standing entity on such a surface, your weight would be something like 10 billion times what it is now. Nothing with atoms in it, nothing held together by chemical bonds or molecular forces, or even metallic bonding, survives for a moment in such gravity. You would be flattened, not just to the ground, but into the ground, your atoms driven downward with a force that makes the concept of structure inapplicable. Below the thin atmosphere lies the outer crust. This is the first solid layer, solid being used loosely, because the material here is unlike any solid on Earth. The crust of a neutron star is composed primarily of atomic nuclei arranged in a crystalline lattice, a structure where the nuclei are fixed in regular geometric patterns. Surrounded by electrons that are not bound to any particular nucleus, but instead flow freely through the lattice like a gas. This is not so different from ordinary metals, where electrons are also shared freely among atoms. But the nuclei in a neutron star crust are not ordinary nuclei. They are far more neutron-rich than any nucleus you would encounter in stable matter on Earth. While a nuclei contains 26 protons and 30 neutrons, the nuclei in a neutron star's outer crust might contain, say, 36 protons and 120 neutrons, far more neutrons than protons, squeezed into an increasingly strange configuration by the immense pressure forcing electrons into protons to create more neutrons. The crust of a neutron star is the strongest material in the known universe. It has a shear modulus, a measure of resistance to deformation, approximately 10 squared 0 times greater than ordinary steel. If you tried to deform the neutron star crust by any amount comparable to what an earthquake produces in ordinary rock, you would need forces of a kind that do not exist in normal matter. Neutron star crusts are so rigid that when they do fracture, and they do fracture occasionally, in catastrophic events called starquakes, the released energy is staggering. A typical earthquake on Earth releases energy on the order of 10 to 15 to 10 to 17 joules in the most powerful events ever recorded. The 2004 Indian Ocean earthquake, which triggered the devastating tsunami, released approximately 10,017 joules, 100 quadrillion joules. A neutron star quake, in which the crust shifts by a tiny fraction of a millimeter, literally a millimeter or less, can release energy on the order of 10,444 joules. That is roughly 10 squared 7 times more energy than the Indian Ocean earthquake. One followed by 44 zeros in joules. In the fraction of a second it takes for the crust to settle into its new configuration, a neutron starquake releases more energy than the sun will emit in hundreds of thousands of years. We have direct evidence of this. On December 27, 2004, coincidentally 2 days after the Indian Ocean earthquake, a starquake on a specific type of neutron star called a magnetar, located 50,000 light-years away in our own galaxy, sent a burst of gamma radiation toward Earth. 50,000 light-years, a span of space so vast that if you drove at highway speed without stopping, it would take you roughly 300 quadrillion years to cross it, more than 20 million times the current age of the universe. And yet, the gamma-ray burst from that starquake, diluted across 50,000 light-years, was intense enough to measurably affect Earth's ionosphere, the electrically charged upper layer of our atmosphere. Roughly 60 to 1,000 kilometers above the surface, it was the brightest transient event ever detected from outside our solar system, and it came from something whose crust shifted by less than a millimeter. That is the surface you are touching. As you descend through the crust, you feel, in the thought experiment, the material changing around you. The outer crust, relatively accessible to nuclear physics as practiced on Earth, gives way to the inner crust with its nuclear pasta phases. Nuclear pasta is not a whimsical term. The phases of nuclear matter in the inner crust are named for the shapes they resemble. Nuki refers to the phase where the matter exists as roughly spherical nuclei. Spaghetti refers to the phase where nuclei elongate into long cylinders, strands of nuclear matter stretching through the surrounding neutron-rich fluid. Lasagna refers to the flat, sheet-like phase where nuclear matter organizes into planar slabs alternating with voids. Swiss cheese is what you get on the other side of the transition. Instead of blobs or tubes of nuclear matter surrounded by neutron fluid, you get a continuous nuclear matter matrix perforated by cylindrical or spherical holes. Finally, as you approach nuclear density, the distinction between phases vanishes entirely. The boundary dissolves. You have entered the outer core. In the outer core, neutrons are no longer bound into nuclei, but flow freely as a fluid, and this fluid is a superfluid. A superfluid is a fluid with zero viscosity. It flows without any internal friction whatsoever. On Earth, we can create superfluids in the laboratory. Liquid helium-4, cooled to below 2.17 Kelvin, becomes a superfluid. It can flow uphill, climb the walls of containers, and pass through holes so small that no ordinary fluid could move through them. The neutrons, in the outer core of a neutron star, are superfluid not because they are cold. Neutron stars can have interior temperatures of millions to hundreds of millions of degrees, but because of Cooper pairing, a quantum mechanical phenomenon in which pairs of neutrons link up under the attractive component of the nuclear force and condense into a collective quantum state. The pairs, unlike individual neutrons, are bosons, particles that can all occupy the same quantum state, and they condense into a macroscopic quantum coherent state in which all the pairs move together, describable by a single wave function. This is the superfluid. There is no friction because friction requires distinguishable interactions between particles, and in a superfluid there are no distinguishable particles. There is only the collective wave. We have observational evidence for this superfluid. Neutron stars rotate, and they slow down gradually over time as they lose rotational energy to radiation. Occasionally, however, some neutron stars experience a sudden speed up in their rotation rate, a brief but measurable increase in how fast they are spinning. These events are called glitches, and they happen without warning, increasing the rotation rate by a tiny but detectable fraction in a matter of seconds before the star begins slowing down again. The most widely accepted explanation involves the neutron superfluid in the crust and outer core. A superfluid, when it rotates, does not rotate as a bulk flow the way an ordinary fluid does. Instead, it rotates by forming quantized vortices, tiny tornado-like structures, each carrying a fixed quantum of angular momentum. As the neutron star slows, these vortices should gradually migrate outward, coupling their angular momentum to the solid crust. Occasionally, many vortices on pins simultaneously and transfer their angular momentum to the crust in a sudden collective event, and this causes the observable glitch. We are watching quantum mechanics operate inside a star 20 kilometers across, from hundreds of light years away. The Vela pulsar, a neutron star roughly 1,000 light years away, born in a supernova approximately 11,000 years ago, is the most prolific glitcher known, having exhibited more than 24 glitches in the decades since its discovery. Each Vela glitch increases the rotation rate by about 1 part in a million, a tiny fractional change, but one whose recovery time scale, during which the star's rotation rate relaxes back toward the electromagnetic braking trend, tells us what fraction of the star's interior is in the superfluid component. The answer is consistent with a superfluid occupying a substantial fraction of the interior. The star's own stuttering is teaching us what it is made of. There is one more regime of neutron star life worth understanding: the coaling. A newly born neutron star starts at roughly 10 billion Kelvin and cools from 10 billion to 1 billion Kelvin in approximately 10 seconds, driven by the copious emission of neutrinos. Neutrinos are ghostly particles that interact only through the weak nuclear force and gravity, passing through ordinary matter with almost no interaction. Right now, as you watch this video, approximately 65 billion solar neutrinos pass through every square centimeter of your body every second, and you feel nothing. But in a neutron star, the matter is so dense that even neutrinos are trapped for tens of seconds before escaping. They thermalize. They carry away heat. The energy carried away by neutrinos in the first 10 seconds of a neutron star's life exceeds the total energy the sun will radiate in its 10 billion year lifetime by a factor of roughly 10,000. Not slightly, 10,000 times. After this initial neutrino burst, the cooling continues more gradually, over millions and billions of years. The cooling curve, temperature as a function of age, is sensitive to the interior composition. A neutron star with hyperons cools faster. A star with quark matter cools differently still. By observing the surface temperatures of neutron stars of known ages, using X-ray telescopes to measure thermal emission, and using associated supernova remnants, or binary companions, to estimate age, we can compare observed cooling curves to theoretical predictions. The Cassiopeia A neutron star, formed in a supernova whose light reached Earth around 1680 C, was found in 2010 to be cooling faster than expected from standard models. This was interpreted as evidence for neutron superfluidity and proton superconductivity in the core, the first time a phase transition to a superfluid and superconducting interior state was inferred directly from the coding behavior of a specific neutron star. The cold, quiet interior of a dying star, 1,000 years old, 11,000 light years away, is still telling us things we did not know. The protons in the inner core, if theoretical models are correct, are also in a special state. They are in a superconducting state, the electromagnetic analog of superfluidity. Protons are electrically charged, so a superfluid of proton-Cooper pairs is also a superconductor, a material in which electric currents flow without resistance, and in which magnetic fields are confined to quantized filaments called flux tubes. The neutron star's interior is threaded by these flux tubes, and it is the slow migration of these flux tubes outward through the superconducting interior that determines how the neutron star's magnetic field weakens over millions of years. The field is not a separate imposition on the star. It is woven into the quantum structure of the matter itself. And neutron star magnetic fields are not small things. A typical neutron star has a surface magnetic field of around 10 million Tesla, 100 million Tesla. The strongest continuous magnetic field ever produced in a laboratory on Earth stands at around 45 Tesla. 100 million Tesla is roughly 2 million times stronger. In the strongest neutron star magnetic fields, those of magnetars, which reach 10 to 10 to 100, 10 to 111 Tesla, the field is strong enough to do something remarkable. It distorts the electron clouds of atoms. Chemistry does not work in a magnetar's magnetic field. The atoms themselves are deformed, their electron clouds compressed along the field lines into thin ellipsoidal shapes, making molecules impossible because molecular bonds require normally shaped electron clouds to form. In the strongest known magnetic fields on neutron star surfaces, the very concept of chemistry, the science of how atoms combine, becomes inapplicable. You cannot have DNA there. You cannot have proteins. You cannot have life as we understand it, because life is molecular machinery, and molecular machinery requires atoms to have normally shaped electron orbitals. And those orbitals exist only in the absence of the magnetic fields that magnetars produce as a matter of course. Pulsars, the broad category of rotating neutron stars that emit detectable beams of electromagnetic radiation, were discovered on November 28, 1967, by Jocelyn Bell Burnell, a graduate student who noticed a regular, repeating signal in the output of a radio telescope she had helped construct in Cambridge, England. The signal pulsed with a period of 1,333 seconds, so perfectly regular that it was initially nicknamed LGM1 for Little Green Men, because no known natural process produced signals that periodic. It was not intelligence. It was a neutron star rotating 0.75 times per second, its magnetic pole sweeping past Earth once per rotation, like a lighthouse in the dark. Bell's supervisor, Anthony Hewish, received the Nobel Prize for the discovery in 1974. Bell did not. She has since received numerous other honours, but the exclusion remains one of the most discussed controversies in the history of the Nobel Prize. She found it. She recognised it. She was 24 years old, working on a PhD, and she changed astrophysics permanently. The fastest rotating pulsars are called millisecond pulsars, and they spin hundreds of times per second. The fastest known millisecond pulsar, PSR J1748-2446 AD, rotates 716 times per second. The equator of this neutron star, a circle roughly 40 kilometers in circumference, is moving at approximately 24% of the speed of light. The surface of this star is moving at roughly 72,000 kilometers per second. In one rotation, which takes about 1.4 milliseconds, 1.5 thousandths of a second, the equatorial surface travels 40 kilometers. It does this 716 times every second. This is the fastest known rotation rate of any object with physical structure in the universe. The star is so close to the rotational breakup limit, the speed at which centrifugal force would overpower gravity and the star would begin to shed material from its equator, that it operates in a regime with the oblate shape of the star. The frame dragging of space-time and the tidal deformability of the nuclear matter all interact in ways that require full general relativistic treatment to describe correctly. These pulsars are clocks, not metaphorically. They are the most precise natural clocks in the known universe. The most stable millisecond pulsars rival atomic clocks in their regularity, drifting by no more than a few microseconds over thousands of years. This stability is not accidental. It is the product of enormous rotational inertia. A body with the mass of the Sun, compressed into 20 kilometers, has so much angular momentum that the only thing that can slow it down on human timescales is the steady electromagnetic radiation it emits. Nothing stochastic, nothing random, nothing thermal, disturbs it in any significant way. The crust is so rigid that starquakes are rare, and even starquakes, catastrophic in energy release, change the rotation rate by only a few parts in a billion. This precision has been weaponized by science. A pulsar timing array, an international network of radio telescopes, all precisely tracking the arrival times of pulses from dozens of millisecond pulsars scattered across the galaxy, is a gravitational wave detector. Not the kind LIGO and Virgo are, which detect high-frequency waves from merging compact objects. A pulsar timing array detects gravitational waves with wavelengths of light-years, years-long oscillations in the fabric of space-time, produced by the orbital inspiral of pairs of supermassive black holes in the cores of distant galaxies. When such a gravitational wave passes through the galaxy, it slightly stretches and compresses the distances between Earth and the pulsars, shifting the arrival times of the pulses by tiny amounts. In 2023, multiple independent pulsar timing array collaborations in North America, Europe, India, Australia, and China announced evidence for exactly this gravitational wave background. The neutron stars, arrayed across thousands of light years, were listening to the low-frequency gravitational hum of merging supermassive black holes throughout the observable universe's history, and we were listening to them listening. The galaxy-scale gravitational wave detector has been operating for decades. We just recently started being able to hear what it was recording. Now, the inner core. The inner core of a neutron star is the most uncertain, most contested, most actively debated region in all of astrophysics. The density at the center is somewhere between 5 and 10 times the density of an ordinary atomic nucleus. But we do not know what form of matter exists there, and the candidates are extraordinary. The standard expectation is that the core consists primarily of neutrons, hence neutron star, possibly with a significant fraction of protons and electrons, and possibly with some hyperons. Hyperons are particles like neutrons and protons, collectively called baryons, but heavier, containing strange quarks in addition to the up and down quarks that make up ordinary protons and neutrons. A lambda hyperon, for instance, contains one up quark, one down quark, and one strange quark. Under the extreme pressures of a neutron star core, it may actually be energetically favourable for neutrons to convert into hyperons, because the Pauli exclusion principle, the quantum mechanical rule that says no two identical fermions can occupy the same quantum state, is filling up all available states for neutrons, and creating a heavier hyperon uses a different slot in the quantum state space. The presence of hyperons in neutron star cores is actively debated, and there is something called the hyperon puzzle. Models that include hyperons in the core tend to predict neutron stars that are less rigid and have lower maximum masses, which conflicts with the observed existence of neutron stars as massive as 2 solar masses. But hyperons may not be the most exotic inhabitants of the neutron star core. There are models, serious, peer-reviewed, mathematically rigorous models, that predict the existence of quark matter at the center of the most massive neutron stars. Quarks are the fundamental constituents of hadrons, of protons, neutrons, and hyperons. Normally, quarks are confined inside hadrons and cannot exist freely. This is called confinement, and it is one of the fundamental properties of the strong nuclear force. But at sufficiently high densities, the hadrons may be so compressed that the quarks are no longer clearly inside any particular hadron. They become, effectively, free. They exist in a state called quark matter. This state of matter, if it exists in neutron stars, would make those objects not really neutron stars at all. They would be quark stars, or hybrid stars with quark matter cores surrounded by hadronic matter envelopes. This is speculative, but the speculation is grounded in serious theoretical work. There may be at the very center of the most massive neutron stars a state of matter called a color superconductor. In ordinary superconductivity, electrons pair up into Cooper pairs, and the condensate carries no electrical resistance. In a quark matter color superconductor, quarks pair up under the strong nuclear force in a way governed not by electrical charge, but by color charge, the charge that quarks carry in quantum chromodynamics. The most exotic predicted phase is the color-flavor locked phase, in which a deep symmetry emerges between the flavor of the quarks and their color charge, producing a condensate that is both superfluid and superconducting with respect to the strong force, and which has properties unlike any other known state of matter. If this exists at the center of massive neutron stars, it is a phase of matter that existed throughout the entire universe for only the first microsecond after the Big Bang, when temperatures were so high that quarks were free everywhere, and which has never existed anywhere at equilibrium since, except here. Except in these quiet spinning objects in the dark, 20 kilometers wide, maintaining in their centers a condition that the universe itself could not sustain for more than a microsecond at its own birth. The universe keeps copies of its own history in the centers of neutron stars. We have been discussing what a neutron star is in isolation, but most neutron stars are not isolated. Many of them are in binary systems, locked in orbital dances with companion stars, accreting matter, exchanging mass, evolving together over billions of years. And it is through these binary systems that some of the most remarkable phenomena of neutron star astrophysics emerge. When a neutron star accretes matter from a companion, capturing hydrogen and helium from the companion star's outer layers as it overflows its gravitational sphere of influence, that matter falls toward the neutron star and arrives at its surface at velocities that are a significant fraction of the speed of light. The kinetic energy released when this matter impacts the surface is enormous. The efficiency of this process, the fraction of the infalling matter's mass energy converted to radiation, is between 10 and 20%. Nuclear fusion, by comparison, converts about 0.7% of mass to energy. Chemical combustion converts about 1/10,000,000%. Accretion onto a neutron star is literally 1,000,000 times more efficient at extracting energy from matter than burning. The luminosity of a bright accreting neutron star can reach 100 times the luminosity of the Sun, produced by a region 20 kilometers across. Per unit area, this exceeds the surface of the Sun by a factor of roughly 1 trillion. This accretion process produces type 1 X-ray bursts. As hydrogen and helium accumulate on the neutron star's surface, the pressure and temperature at the base of the accumulating layer increase until conditions become sufficient to ignite thermonuclear fusion. On a neutron star, this ignition does not produce a steady glow. It propagates across the entire surface in a matter of seconds, a thermonuclear flash engulfing the whole star in less time than it takes you to blink. The luminosity during such a burst can briefly reach 1,000,000 times the Sun's luminosity, then fades over seconds to minutes as the fuel is consumed. These bursts recur every few hours to days as the layer rebuilds. We observe them routinely with X-ray telescopes, watching a star in a distant part of the galaxy light up like a nuclear flashbulb and fade, light up and fade, every few hours, from thousands of light years away. And here is where gold enters the story, not as a metaphor, as a product. The collision of two neutron stars is one of the primary sites, perhaps the primary site, for the production of heavy elements in the universe. Gold, platinum, uranium. The elements heavier than iron that cannot be made by stellar fusion, but instead require an extreme environment with a sufficiently high density of free neutrons to be captured by atomic nuclei in rapid succession, the ARC process, or rapid neutron capture process, are made when neutron stars die. During the merger of two neutron stars, a small but significant fraction of the total mass, perhaps a few percent, is ejected as neutron-rich material moving at 1/10 to 1/3 of the speed of light. This ejector is the R process factory. In the seconds to days following the merger, rapid neutron capture builds up atomic nuclei through the periodic table from iron to uranium and beyond, synthesizing the elements that no other astrophysical process can efficiently produce. The gold in your jewelry, the platinum in catalytic converters, the iridium and the geological boundary layer that marks the end of the Cretaceous period. These elements were forged in neutron star mergers that happened billions of years ago, in galaxies far away, and their ejector eventually became part of the nebula that collapsed to form our solar system. You are wearing a neutron star. You have always been wearing a neutron star. The gold on your finger is the wreckage of a collision between two city-sized objects of pure nuclear matter, a collision that released more energy in milliseconds than the sun will produce in its entire 10 billion year lifetime. A collision that happened before the Earth existed, in a galaxy that may no longer exist, and whose output, scattered across the cosmos, eventually found its way into the crust of our planet, into the veins of quartz and granite, into the ground beneath human civilization, into the hands of whoever first learned to work metal. We watched such a collision happen. On August 17th, 2017, gravitational wave detectors at LIGO and Virgo, the Laser Interferometer Gravitational Wave Observatory, whose kilometre-scale laser arms can detect a displacement smaller than 1/10,000th the diameter of a proton, recorded a gravitational wave signal lasting approximately 100 seconds, rising in frequency and amplitude, produced by two neutron stars spiraling together at 130 million light-years. The light from this event had been travelling since before the first dinosaur walked on Earth. It arrived in the form of a gravitational wave and a gamma-ray burst and an optical infrared afterglow, all arriving within seconds of each other from the same point in the sky. The kilonova, the optical and infrared glowing cloud of freshly synthesized heavy elements expanding from the merger at a fraction of the speed of light, was observed by telescopes on every continent and in space. Spectroscopic analysis of the kilonova identified the signatures of strontium and other heavy elements in the ejector. The Rye process was confirmed. The gold factory was seen operating. For the first time in history, we watched heavy elements being made in real time in a collision we had been tracking with gravitational waves for the preceding 100 seconds. From that single event, GW 17871, astrophysicists extracted an independent measurement of the Hubble constant, the rate at which the universe is expanding. They constrained the neutron star equation of state from the tidal deformability measured in the gravitational wave signal. They confirmed that gravitational waves travel at the speed of light to 1 part in a quadrillion, ruling out entire classes of alternative gravity theories. They confirm the kilonova model of R-process nucleosynthesis. And they did all of this from a single observation lasting a few days of an event that happened 130 million years ago in a galaxy called NGC 4993 in the constellation Hydra. This is what we can do now. This is the era we are living in. Now, stepping back from the broader universe and returning to the question we began with, what happens to you? Let us trace the final stages of the descent with full precision, now that we have all the context we need. Not abstractly, not with vague gestures at extremity. Step by step, layer by layer, from the moment the tidal forces begin their work to the moment the last trace of your identity as organized matter dissolves into the extreme physics of the interior. You begin to fall from rest at some considerable distance, let us say 10,000 kilometers from the neutron star surface. At this distance, the gravitational acceleration you feel is already roughly 500,000 Gramses, 500,000 times the gravitational pull of Earth. You are not just falling. You are accelerating with a force that no rocket ever built by human hands could resist for more than a fraction of a second. In the first moments of the fall, your body remains structurally intact because the tidal gradient across your 2-meter height is not yet catastrophic. You feel an intense pulling sensation, as though your feet are enormously heavier than your head, which they are, by a significant and increasing amount. Your circulatory system strains. The blood does not circulate evenly. At these accelerations, even the strongest bones in the human body begin to compress and shift in ways they were not designed for. At roughly 1,000 kilometers out, you are moving at tens of thousands of kilometers per second, a significant fraction of the speed of light, acquired through free fall from 10,000 kilometers. Your body has by now been subjected to tidal stresses of thousands of grams across its length. Your skeleton has failed. Your organs have detached from one another. You are no longer a body in any functional sense, but the matter is still largely intact. Bones, tissue, molecules, atoms, all of it still in roughly the same positions, simply no longer held together by biological structure. At a few hundred kilometers, the tidal force gradient is in the millions of grams across your body's former length. The molecular bonds holding tissue together, covalent bonds, hydrogen bonds, the weak electrostatic interactions that maintain protein structure, are overwhelmed. You are now a cloud of organic molecules, amino acids, fragments of DNA, lipid molecules, water, inorganic salts. The cloud is elongated radially, already several kilometers long in the direction of fall and only a few meters wide transversally, squeezed by the lateral component of the tidal force that compresses as it stretches. This cloud heats rapidly. Compression heats gas. The cloud of organic molecules is being compressed laterally while accelerating toward the neutron star, and the kinetic energy of the compression becomes thermal energy. At 100 kilometers out, the temperature of the infalling material has climbed to tens of thousands of degrees. At this temperature, organic molecules break down entirely, not into atoms, but first into smaller fragments, then into atoms as the temperatures climb further. At 1,000,000 degrees, atoms lose their electrons. Your matter is now a fully ionized plasma, free electrons, and bare atomic nuclei. The nuclei of carbon and oxygen and hydrogen and nitrogen that composed your body, stripped of every electron, interacting through pure electromagnetic forces, glowing in X-rays, moving at hundreds of kilometers per second. At 10 kilometers from the surface, the plasma is moving at perhaps 50 to 100,000 kilometers per second, 15 to 30% of the speed of light. The infalling material strikes the neutron star atmosphere at this velocity. The kinetic energy per nucleon, per individual proton or neutron, at these velocities is comparable to the energies achieved by particles in the Large Hadron Collider at CERN, the most powerful particle accelerator ever built. Not slightly comparable. Comparable in order of magnitude. Your atoms are arriving at the neutron star surface with particle accelerator energies, and there are vastly more of them than any accelerator has ever processed. The impact is not a gentle landing. It is a thermonuclear event. Your atoms, what remains of you after tidal disruption, heated to plasma temperatures, ionized and compressed into a radially elongated stream, arrive at the neutron star surface as bare atomic nuclei. The nuclei slam into the crystalline lattice of the outer crust with kinetic energies far exceeding anything achievable in particle accelerators on Earth. They are incorporated into the crust, adding to it, changing the isotopic composition of the outer layers, triggering thermonuclear reactions in the accumulated fuel. The matter that was by becomes part of the neutron star. Your carbon and oxygen and nitrogen nuclei survive the incorporation. Initially, they are pressed into the outer crust, surrounded by other neutron-rich nuclei in the crystalline lattice. Over thousands of years, as the accumulating layers above them grow, they migrate deeper, subjected to increasing pressure. The nuclei begin to grow neutron-rich, electrons forced into protons by the pressure, converting carbon into increasingly exotic neutron-rich isotopes that exist nowhere else in the known universe except inside neutron stars. The periodic table, which on Earth ends at Oganesson with 118 protons, becomes meaningless as a guide to what is happening here, because the matter has moved past the boundary of what the periodic table was designed to describe. Further, deeper, into the nuclear pasta region, the nuclei that were your atoms begin to merge with their neighbours, losing their spherical shapes, elongating into nuclear spaghetti, alongside countless other nuclei doing the same thing. The individual identity of the nucleus that used to be part of a carbon atom in your left hand dissolves into the collective structure of a strand of nuclear pasta shared among the nuclei of the entire inner crust. Then the pasta phases transition to the neutron fluid of the outer core, and there the final individual nuclear identities dissolve entirely. Your matter joins the neutron superfluid, not metaphorically, literally. The nucleons that compose the atoms of your body have been converted by pressure into neutrons, and those neutrons have joined the macroscopic quantum condensate of the neutron superfluid, described by a single quantum wave function shared among all the neutrons in the outer core. The boundary between the matter that was you and the matter of the neutron star has become a meaningless distinction. There is only the superfluid. There is only the wave function. The quantum mechanics of neutron pairing does not know the difference between a neutron that was once part of a carbon atom in a human heart and a neutron that has been part of this star since its formation 2 billion years ago. They are identical particles. They enter the same condensate. The condensate is unchanged, except by a fraction too small to measure, in the direction of greater mass and slightly greater radius. And then, over millions and billions of years, if the neutron star is isolated, not accreting, just cooling, the matter that was you cools along with the star. The neutron fluid, already a superfluid, remains so as the temperature drops. The crust solidifies ever more completely. The magnetic field decays, slowly, as the quantized flux tubes in the superconducting proton fluid migrate outward and eventually escape the star entirely, over timescales of tens of millions to hundreds of millions of years. The pulsar, if this star has the geometry to be a pulsar visible from somewhere, gradually slows. The pulsars lengthen in period. The X-ray luminosity fades. Eventually, the star dims below the detection threshold of any instrument in any plausible civilization. It continues, dark and cold and dense, traveling through the galaxy, a city-sized ball of nuclear matter, moving at a few hundred kilometers per second, part of the galactic disk, orbiting the center of the Milky Way every quarter of a billion years, crossing the spiral arms, accumulating small amounts of interstellar hydrogen on its surface, radiating nothing of significance, existing completely. The matter that was you will do this for far longer than the current age of the universe. The neutron star's cooling time scale to temperatures below detection is roughly a billion years. After that, it travels as a dark neutron star, accreting tiny amounts of hydrogen from the interstellar medium, never reaching the critical mass to reignite or to collapse, moving through the increasingly empty and dark late universe. In 10 trillion years, 1,000 times the current age of the universe, when the last stars are burning out and the Milky Way is a sparse collection of white dwarfs and black holes and cold remnants, the matter that was you is still there, still in that neutron star, still nuclear matter, still dense, still travelling. Still, unless before that, the star crosses the critical mass and collapses into a black hole. If enough interstellar gas accretes, or if the neutron star merges with another compact object, the mass exceeds the maximum supported by neutron degeneracy pressure. The collapse takes a fraction of a millisecond. The event horizon, the boundary from within which nothing can escape, forms and expands to its final size in the time it takes a light beam to cross the neutron star's diameter, about 0.4 seconds. The matter that was you crosses the event horizon. From your reference frame, if such a thing persisted, the crossing of the horizon is invisible. No flash, no announcement, no warning. The geometry of space-time has changed around you, but you cannot detect the change locally. You can only know it from the outside, and from the outside, you are never seen to cross. From outside, you appear to slow as you approach, the light from your position redshifting toward invisibility, your clock appearing to slow toward zero as gravitational time dilation approaches infinity at the horizon. You fade. You are never seen to cross. You simply become too dim and too redshifted to observe, frozen in time at the edge of the horizon from the perspective of the outside universe, though in your own reference frame, you long since passed through. Inside the event horizon, the direction toward the singularity becomes a future direction in space-time. It is not possible to avoid the singularity any more than it is possible to avoid tomorrow. Time flows toward it. Space flows toward it. All world lines, all possible paths through space-time converge on it. The matter that was you, nuclear matter now, part of what was the neutron star, arrives at the singularity. What happens there is unknown. General relativity predicts infinite density and infinite curvature. General relativity is wrong at this point, in the sense that every theory is wrong at the boundary of its domain of applicability. Quantum gravity, the theory that correctly describes the physics of the Planck scale, where quantum mechanics and general relativity must both be relevant, does not yet exist in a complete, tested form. String theory has something to say about it. Loop quantum gravity has something to say about it. The different theories mostly agree on what happens outside the horizon and disagree about the interior. The interior of a black hole, from the singularity to the horizon, is the frontier of physics, the region where all our current theories break down, where the next theory has not yet been written. We do not know what happens to your matter at the singularity, not because we have not thought about it, because the physics does not yet exist to describe it. That is an honest answer. It is also, in its own way, an extraordinary one. The fact that there is a question the current physics cannot answer, that there is a region of the universe where the best theories we have, built on a century of experiment and mathematics, are known to fail, is not a failure. It is a frontier. It is the shape of what is left to understand. Every generation of physicists has had such frontiers, and every generation has had its theories fail at the edge and been compelled to construct better ones. Newton's mechanics failed at high velocities, and special relativity replaced it. Special relativity could not describe gravity, and general relativity replaced it. General relativity fails at the singularity, and quantum gravity will eventually replace it there. The sequence is not random. It is directed, consistently, toward greater precision, greater scope, greater depth. Each failure reveals the structure of the next theory. The singularity is telling us what quantum gravity needs to describe. We are listening. Now consider the neutron star as a whole, not just as a place you fall into, but as an instrument. Consider what it has taught us. The discovery of pulsars confirmed the existence of neutron stars. The precise timing of pulsars measured the slowing of the orbit of a binary pulsar, the Holtz-Taylor binary, and confirmed that the system was losing energy at exactly the rate predicted by general relativity for gravitational wave emission, providing the first indirect evidence for gravitational waves in 1974, confirmed in detail over the following decades. The observation of GW1 70817 confirmed that gravitational waves travel at the speed of light, that R process nucleosynthesis occurs in neutron star mergers, and provided an independent measurement of the Hubble constant. Pulsar timing arrays have now detected the gravitational wave background from merging supermassive black holes throughout the universe's history. X-ray observations of neutron stars in binary systems have constrained the equation of state of dense nuclear matter. Observations of glitches have provided evidence for neutron superfluidity in the interior. The December 2004 magnetar burst constrained the maximum neutron star magnetic field and provided evidence for the starquake mechanism. At every stage, neutron stars have served as nature's own extreme physics laboratory, running experiments on dense matter and strong gravity that no human technology could replicate, and broadcasting the results in electromagnetic and gravitational radiation for us to decode. We are the decoders. We did not build the laboratory, but we have been learning to read it, one observation at a time. Over the 60 years since that November night in Cambridge, when a graduate student noticed an anomaly in her paper chart output and did not dismiss it as noise. There is something in that story, in the image of Jocelyn Bell in 1967, analysing paper chart output in a radio observatory in Cambridge, and finding in that data the first neutron star that deserves to be held up. The neutron star did not announce itself. It broadcast, as it had been broadcasting for millions of years, indifferent to whether anyone was listening. Bell was listening. And because she was, and because she looked carefully at what she heard, we know what neutron stars are. We know they exist. We know they spin. We know they have superfluid interiors and magnetar-strength magnetic fields and rotate 716 times per second and produce the gold in our jewelry and collapse into black holes and ripple the space-time of the galaxy. We know all of this because someone was careful, because someone looked at a piece of paper with a strip chart signal on it and thought, this is strange, and strange things deserve attention. The neutron star does not care that we know. It spins on. PSRJ 1748-2446. AD is rotating right now in the direction of Sagittarius, 18,000 light years from Earth. It has made approximately 20 billion complete rotations since the formation of our solar system. 20 billion, which is about the same order of magnitude as the number of heartbeats in a human lifetime if you lived for 5 million years. It will make 20 billion more in the next 12 million years. It will be spinning and pulsing long after the sun has become a white dwarf and the Earth has been consumed and the last mammals have lived and the last bacteria have gone quiet. It will be spinning when the Milky Way and Andromeda merge in about 4 billion years. It will be spinning when the resulting galaxy has settled into an elliptical shape and most of its star formation has ceased. It will be spinning in the dark, with no audience, with no listener, its radial beam sweeping through empty space that contains no radio telescope, no civilization, perhaps nothing capable of receiving a signal. It does not need an audience. It never did. It only needs a wave function and a magnetic field and an angular momentum and the laws of physics that have operated unchanged since the first second of the universe's existence. The atoms in your body and the atoms in that neutron star are made of the same quarks, governed by the same forces, subject to the same equations. The only difference is arrangement, density, history. You are a particular arrangement of the universe's matter, one in which the quarks have organized themselves into atoms, the atoms into molecules, the molecules into cells, the cells into a nervous system capable of modeling the outside world, and the nervous system into a mind capable of asking what would happen if it fell into a neutron star. The neutron star is a different arrangement, simpler in some ways, more extreme in others, less structured but more compressed, a particular solution to the same equations of physics that describe you. When you contemplate a neutron star, you are matter contemplating a different arrangement of itself. You are the universe using one of its configurations to examine another. This is not a metaphor designed to comfort you. It is a description of what is actually happening when you think about physics. The quarks in your neurons are firing in patterns that model a distant object made of different quarks in different patterns, and the model is accurate enough to predict observational consequences, and those predictions match the observations. And the matching is not coincidence. It is the signature of a universe that is internally consistent, that operates by the same rules everywhere, that is knowable through careful observation and honest mathematics. That is what science is. That is what neutron stars are. That is what you are, briefly and remarkably, in the dark. You are matter that has learned to look at itself. You are atoms that have arranged themselves into a configuration capable of wondering about atoms arranged in different configurations. You are a temporary knot in the fabric of a universe that is mostly undifferentiated plasma and dark matter and empty space, and not complex enough to feel the weight of what it does not know and to work out low well. What is the market of benchmark? The neutron star has no such complexity. It has only density and spin and time. And for that span, the neutron star was understood, a little more than before. The universe, in that moment, examined itself. That is enough. That is, in fact, extraordinary.